Welcome to the deep dive. Today, we're looking way up at the stars that, well, don't quite sit still, variable stars.
That's right. Not the constant points of light you might imagine. These actually change their brightness over time.
And it's not just a few, right? We're talking about huge numbers.
Absolutely. Hundreds of thousands are known. It's a pretty common phenomenon, actually.
So, for this deep dive, we want to unpack why they vary and how missions like Gaia are helping us figure it all out.
Exactly. And broadly speaking, there were two main flavors here: intrinsic and extrinsic variability.
Okay, intrinsic means the change comes from inside the star itself.
Correct. The star's own physical processes are causing the brightness to fluctuate. Think pulsations, eruptions, that kind of thing.
And it's extrinsic.
That's when something outside the star affects the light we see. Maybe something blocking the light or
Yeah.
bending it.
Got it. So, Gaia, this amazing space observatory, it's a big player in this field.
A huge player. Its view from space, above the Earth's atmosphere, gives it this incredible all-sky visibility and unprecedented accuracy in measuring brightness. Photometric accuracy, we call it.
So it's not necessarily seeing stars more often than ground telescopes, but the quality is just way better.
Precisely. That clarity is key. So yeah, let's dive into how Gaia spots these variations and what we're learning.
Okay, let's start with those intrinsic changes. You mentioned pulsating stars.
Yeah, that's a major category. These stars literally get bigger and smaller rhythmically. They expand and contract.
Like they're breathing, a cosmic breath.
Yeah, that's a good analogy. It's this constant push and pull between the outward pressure from the energy generated inside and the inward crush of gravity. Gas opacity plays a big role, too.
Fascinating. And I guess they don't all breathe the same way.
Not at all. There's a whole zoo of them. You have Seraphides and RR Lyrae stars, super important, those ones,
Why are they so important?
because their pulsation period, how long one cycle takes, is directly linked to how bright they truly are, their intrinsic luminosity.
Ah, the standard candles for measuring distances.
Exactly. Cosmic yardsticks. Then you've got others, Delta Scuti, SX Phoenicius, mirror variables, which are these really long period, large amplitude pulsators, Beta Cephei, Gamma Doradus, loads of types.
Wow. Different time scales, different amounts of brightness change.
Yeah, really diverse. Some even pulsate in multiple ways at once. It gets complex.
Okay, so pulsations are one kind of internal change. What about the more dramatic ones, eruptive variables?
Right. These are less predictable, often more irregular, sometimes really sudden changes.
What causes those?
Often it involves the star shedding mass, maybe in big outbursts, or sometimes it's accreting material pulling gas off a nearby companion star, for instance.
So this includes things like flares.
Yep, flare stars can brighten dramatically very quickly, and then you have the really explosive ones, cataclysmic variables.
That sounds intense.
It is. Think novae, dwarf novae, and the ultimate fireworks, supernovae, where a star basically destroys itself.
Incredible power. So even our sun, which seems pretty steady to us,
Yeah.
has a very...
It does, yeah, but very subtly compared to these others. It has the well-known 11-year solar cycle linked to its magnetic activity. That causes tiny brightness changes.
Okay, minuscule changes.
Very small. And if you look really, really closely, there are even these super short 5-minute oscillations driven by convection, the bubbling motions near the surface, like the sun is kind of murmuring.
Amazing. Okay, so that covers the intrinsic side changes within the star. Let's switch to extrinsic. What's happening outside the star?
Right, so here, the star's light output might be fairly constant, but something is interfering with that light reaching us.
Like what?
Well, rotating stars, for one. If a star has big star spots, like sunspots, but potentially much larger,
Okay.
as the star spins, those darker spots rotate into view and then out again, causing a periodic dip in the brightness we see.
Makes sense, like a lighthouse with a dark patch on the bulb.
Kinda, yeah. Also, some stars spin so fast they bulge out at the equator, becoming ellipsoidal, sort of like a rugby ball shape.
Not perfectly round.
Exactly. And as that shape rotates, we see a slightly different surface area, which also causes brightness variation.
Never. What else?
Eclipsing binaries are a big one. Really common, actually. Two stars orbiting each other.
And one passes in front of the other from our perspective.
Precisely. When one star eclipses its partner, it blocks some light, causing a distinct regular dip in the total brightness we measure. A cosmic shadow play.
And that's related to how we find planets around other stars, isn't it? The transit method.
Exactly the same principle. When an exoplanet passes in front of its host star, a transit, it causes a tiny, tiny dip in the starlight.
Super tiny, I bet.
Oh yeah, very small. But missions like Kepler and now TESS and even Gaia can detect these dips. It's how we've found thousands of planets.
So Kepler was really the king of that.
Kepler was revolutionary for exoplanet transits,
Yeah.
absolutely. Gaia contributes too, though its main strengths lie elsewhere.
And you mentioned one more extrinsic type, lensing.
Gravitational lensing, yeah, it's rarer for variability. But if a massive object, like another star or even a black hole, passes between us and a distant star,
Its gravity bends the light.
right, it acts like a lens, potentially magnifying the background star, causing its apparent brightness to fluctuate as the lensing object moves. Pretty cool, but less common than eclipses or rotation.
So people have been seeing stars flicker for ages. How did we go from just noticing it by eye to these huge surveys?
Well, yeah, it started with naked eye observations. Ancient astronomers noting stars that seemed to appear, disappear, or change brightness. Meticulous record keeping.
Must have taken patience.
Immense patience. Then telescopes obviously helped enormously. And astronomical photography was a game changer, getting permanent records.
And now,
Now we have these large-scale robotic surveys. Pan-STARRS, ASAS, the All-Sky Automated Survey, they scan huge chunks of the sky repeatedly.
night after night.
Exactly. Building up timelines of brightness for millions, even billions of stars. That lets us catch variations we'd otherwise miss. And the Vera Rubin Observatory is going to take this to a whole new level soon.
So where does Gaia really shine in this modern era of surveys? You mentioned its accuracy.
Yes, that's its superpower. Being in space, it avoids the blurring and dimming effects of Earth's atmosphere. Ground-based surveys fight that constantly.
Right, the twinkling is nice poetically, but bad for precision measurements.
Exactly. Gaia gets this incredibly clear view. So while it might not stare at one patch of sky constantly like Kepler did,
It sees the whole sky.
the whole sky, and measures the brightness of stars with phenomenal precision. We're talking millimagnitude accuracy for
Yeah.
many stars.
Tiny fractions of a percent change in brightness.
Even less for the brighter ones, yeah. Down to 0.3 millimagnitudes. It's astonishing.
So while it might pick up some transits or lensing events,
It will, yes.
Hmm.
But its real strength isn't finding those super subtle, rapid oscillations of stars' astroseismology. That's generally below its detection threshold.
Yeah.
But for classical pulsating stars, like Cepheids and RR Lyrae, for many eruptive variables, and especially for eclipsing binaries across the whole sky, Gaia's contribution is just massive. Revolutionary, really.
how does it actually gather the data? Does it just stare or?
It scans. Gaia is constantly rotating, and its two telescopes sweep across the sky in a complex, predefined pattern.
So it revisits stars.
Oh, yes.
Yeah.
Over the initial 5-year baseline mission, a typical star would cross Gaia's focal plane, where the detectors are about 70 times.
70 measurements over 5 years.
On average, yeah. Some areas get more visits, some less, depending on the scanning law. And each time a star drifts across the detectors, its light is measured very carefully.
How long does that take?
The light is integrated over 9 CCD detectors as the star moves across them, which takes about 40 seconds in total for the main brightness measurement.
40 seconds seems quick for such faint objects.
The detectors are incredibly sensitive, and that data, once it's sent back to Earth, goes through a massive calibration process.
To remove instrument effects and get those precise numbers.
Exactly. The main brightness is measured in Gaia's broad G-band. That's where we get the stunning precision, like 0.3 millimags for stars brighter than magnitude 13, maybe 1 millimag at magnitude 17. Still around 6 millimags, even down at magnitude 20.
Still impressive for faint stars. Does it measure colors too?
It does, using blue and red photometers, BP and RP. The precision there is a bit lower than the G-band, but still excellent and crucial for understanding the stars.
And these measurements form the basis of the big data releases.
Correct. Data Release 2, or DR2, used data from July 2014 to May 2016. That EDR3, the early Data Release 3, extended that up to May 2017. And DR3 built further on that.
And DR2, that was the one that really exploded the number of known variable stars.
Oh, absolutely. Gaia DR2 included a specific catalog of variable stars. It contained, get this, 550,737 classified variables.
Whoa, 500,000. Just like that. How many did we know before?
The total number known before Gaia was maybe around 150,000, 200,000 that were well cataloged. So Gaia DR2 basically tripled the number overnight, a fundamental shift.
That's staggering. What kinds of variables made up that 500,000?
A huge mix. There were nearly 229,000 RR Lyrae stars.
Wow, the distance markers.
Yep, and over 11,000 Cepheids, again, crucial for galactic structure and distances. Also about 152,000 long-period variables like those Mira stars,
Okay.
around 148,000 stars showing variability likely due to rotation or spots, nearly 9,000 Delta Scuti and SX Phoenicis types, which are shorter period pulsators, and about 3,000 classified just as short timescale variables.
Just an incredible diversity and volume of data.
And that was just DR2. Later releases like DR3 have added even more, refining classifications and finding new things. The numbers just keep growing.
It must be a monumental task to sift through Gaia's raw data and actually find and classify all these. Who does that?
That falls to the Gaia Data Analysis and Processing Consortium, or DPAC. It's a huge collaboration across Europe.
Okay.
And within DPAC, there's a specific group, Coordination Unit 7, or CU7. Their job is specifically Variable Objects Detection, Classification, Characterization, led by Laurent Ayer.
So CU7 are the variable star specialists for Gaia.
You could say that, yes, they're the detectives finding the changing stars in that sea of data.
Do they work alone?
Oh no, it's highly collaborative. They rely heavily on other CUs. CU5 provides the essential calibrated photometry, the brightness measurements.
Right, the raw material.
Exactly. CU4 deals with binary stars, which is obviously relevant. CU6 handles spectra and radio velocities, giving information about motion and composition. CU8 calculates fundamental stellar parameters like temperature and gravity. They all feed into each other.
A real ecosystem of data analysis.
Definitely. And there's even a team led from Cambridge that scans the data much faster, looking for things that change right now, transients, like supernovae. They send out alerts for quick follow-up from ground telescopes.
Near real-time astronomy. Amazing. So how does CU7 actually process this flood of data? What's the workflow?
It's a pretty complex pipeline.
Yeah.
First, they ingest the photometric data from CU5 for billions of sources. Then they cross-match these sources with existing star catalogs.
See if we already know something about them.
Right. Then comes the core part. Running various algorithms to detect variability. Is this star changing brightness significantly?
Okay.
If it is, then classification modules try to figure out what kind of variable it is based on its light curve shape, period, amplitude, color, and so on.
And then they publish the results.
The results, the classifications, periods, etc., are packaged up and passed to other CUs and eventually released to the world in the Gaia catalogs. And it's not a one-shot deal, it's iterative. As more data comes in from Gaia, they reprocess, refine the classifications, improve the periods.
Must need some serious computing power.
Absolutely. This all runs on a large computing cluster in Geneva, crunching through petabytes of data.
So let's get into the weeds a little. What kind of tricky processing is involved? You mentioned corrections earlier.
Yeah, for instance, all the observation times need to be converted to a standard system, like barycentric Julian date. And crucially, you have to correct for the motion of Gaia itself and the Earth around the solar system's center of mass, the barycenter.
Why is that so important?
Because those motions slightly change the timing of when light arrives. For precise period analysis, especially for short periods, you absolutely have to account for that. It's about wringing every last bit of precision from the data.
Okay, meticulous corrections. Then how do they actually flag a star as variable?
They use statistical tests, essentially asking, is the scatter in this star's brightness measurements significantly larger than what we'd expect just from the measurement errors alone?
Taking into account that fainter stars naturally have bigger errors.
Exactly, and that some stars were observed more times than others. It's sophisticated statistics to separate true variability from noise.
Are there different ways they look for variability?
Yes, there's general variability detection, just finding anything that changes, but also special variability detection modules designed to sniff out specific, harder-to-find signals.
Like what?
Things like very short timescale variations, maybe just hours or less. Very low amplitude changes. The characteristic U-shaped or V-shaped dips from planetary transits or eclipsing binaries. Even subtle signatures of stellar activity cycles, like the sun's.
So tailored searches. And once a variable is found, how is it classified? You mentioned machine learning.
Right. First, they characterize it. If it looks periodic, they use methods like Fourier analysis to find the period, amplitude, and shape of the light curve.
Breaking down the signal.
Yep. Then the classification engine takes over. It uses supervised machine learning algorithms, things like Gaussian mixtures, Bayesian networks, random forests.
How do those work?
They're trained on examples of known variable stars. The algorithms learn the typical features light curve shape, period, amplitude, color, location on diagrams associated with each class, like RR Lyrae or eclipsing binary or rotation modulation.
So they learn to recognize the patterns.
Exactly. Then, when presented with a new variable star from Gaia, The classifier calculates the probability that it belongs to each known class. It makes an automated, statistically based decision.
That's incredible. Automating what used to take astronomers painstaking individual effort.
It's the only way to handle the sheer volume of Gaia data. Humans verify and refine, but the bulk classification has to be automated.
Okay, so we have this massive classified catalog thanks to Gaia and Deepak CU7. What are scientists actually doing with it now? What are the early results showing us?
Well, the scientific exploitation is still really ramping up, but we're already seeing fantastic applications. One key early paper by Laurent Ayer and the CU7 team back in 2019 did something fundamental.
What was that?
They took the 500,000 variables from DR2 and plotted them on a galactic color magnitude diagram.
Ah, the Hertzsprung-Russell diagram, or a version of it, plotting brightness against color, or temperature.
Exactly, it's like a map of stellar evolution. And by placing all these variable stars on the map, you could immediately see where different types of variability live.
So RLRA stars cluster in one area, Cephids in another, Meras somewhere else.
Precisely. It beautifully visualized the regions of the diagram where pulsation, rotation, eclipses, or eruptions are common. It allowed them to characterize the typical properties, the temperature, luminosity, the fraction of stars that are variable, the typical brightness changes for each class, right across the galaxy.
That sounds like a huge step in understanding the physics, linking the variability directly to the star's fundamental state.
It really is. It provides crucial observational constraints for theories of stellar evolution and the physics driving variability. We can see, on a galactic scale, which stars become unstable and why, based on where they sit on this diagram. It gave us new insights straight away.
Just a phenomenal resource. It's like mapping the dynamic population of the Milky Way.
That's a great way to put it. A census of stellar activity and change across our galaxy, revealing patterns we simply couldn't see before.
This has been absolutely fascinating, a real deep dive into how these variable stars work and how Gaia is just revolutionizing our view of them. The scale of it all is just mind-boggling.
It really is. Hundreds of thousands, soon millions of stars cataloged not just by their position and brightness, but by how they change over time. It paints a picture of a very dynamic, living galaxy.
Gaia's data set is clearly a treasure trove. We're probing the physics, the life cycles, the environments of stars in ways that were unimaginable just a decade or two ago.
Absolutely. The precision and the sheer numbers are transformative for stellar astrophysics.
So as we wrap up, it leaves you thinking, doesn't it?
Yeah.
With this flood of data on so many variable stars showing such diverse behaviors, what's hiding in there? What completely unexpected connections or new astrophysical puzzles might emerge as scientists dig deeper into Gaia's legacy?
That's the exciting part. We've mapped the known territories of variability much better, but there are bound to be anomalies, outliers, maybe even entirely new classes of variable objects lurking in the data.
Things that challenge our current models of how stars live and die.
Potentially, yes. It really underscores that the universe is constantly changing, constantly surprising us. Gaia has given us an unprecedented view of that dynamism, and the discoveries are really only just beginning.